Hello everyone. Today we're going to be looking at the questions 29 through 32 in the calculator section of the AP Calculus B final. Starting with question 29, let's get our calculators out and we are ready to go. Okay, the strength of a rectangular wooden beam is proportional to its width times the square of its depth. Find the dimensions of the strongest beam that can be cut from a 15-inch diameter cylindrical log. See diagram at the right. Great. So I'm looking at this, and if we're doing a 15-inch diagonal over here, and our depth and our width are designated this way and this way, vertically, then that means that the Pythagorean theorem is probably going to come into play here, since this is presumably a right triangle. So right away we can say that d squared plus w squared, or let's say w squared plus d squared, is going to be equal to 15 squared. I'm not going to worry about the value of 15 squared. Plenty of time to do that. And then the other formula that we're probably going to need is, well, is going to be this one right here. It's proportional to the strength is proportional to the width times the square of its depth times the square of its depth. So that equals strength, S, is equal to. Now, if it's proportional, that means there's a K, constant of proportionality. And then the width, so K times the width times the square of its depth, like this. So we want to maximize the strength, which means that we're going to need a derivative here. Let's see, we're going to maximize the strength. So we're going to have to solve for either W or D, or if I'm taking a look at this formula, if I'm crafty about it, I can see that there's a D squared here. So really all I need to solve for is D squared. So doing that, we get that d squared is equal to 15 squared minus w squared. And we can use this formula in our strength formula. Substitute that in there like that. So we would be saying that strength, let's see, let's try to get this. After substitution, strength is equal to, well, instead of d squared, we can have 15 minus w squared. Kind of like that. We are almost set for derivatives here. So let's further that along by distributing everything. So we got kW times 15 squared, just using distribution. So we have K, or the strength, is equal to 15 squared times K times W, minus, and again we're distributing, kW times W squared. So that is kW cubed. So again, just distributing kW into this green parenthesis here gives us this. So now we could take the derivative of S with respect to W. So that is ds dw and we should really make that capital S. ds dw is equal to, now 15 squared is just a number, k is just a number, so I can just make that 15 squared k is the derivative of that. Actually, you know what I should do first? Let's see, that is, yeah, I really should have put the derivatives here that I'm taking. So I'm taking the derivative of s with respect to w. Okay, now we'll get back to where we were. The derivative of s with respect to w is just ds dw, and that's going to be equal to, okay, 15 squared is not a w, k is also not a w, so those both act as a constant with respect to w, and a constant times w, the derivative of anything times w, is just, okay, we've got 15 squared k, and then now we just need to take the derivative of kw cubed. Taking this a little bit slower, just remember that w is the variable of differentiation. So this k here, we actually don't need it inside the derivative. We can just stick that on the outside. And now that looks like the ddw of w cubed, which is just, of course, 3w squared. Let's move that 3 up to the front of the, yeah, there we go. And then we're just going to have to set this equal to 0 to find our critical value. And this is, I think, where our calculator is going to come in. You know, before we even do the calculator, let's do one more thing. Let's do a little bit of factoring. These values of k here, they're really not going to help us look for those critical values, so we can factor those out. And well, now this looks pretty good. We just need to solve 15 squared minus 3w squared is equal to 0 with our calculator. Okay, let's do this a couple of different ways. Let's start by putting this in to y1, where we have 15 squared minus 3. We're going to have to change that to an x squared. So 15 to the second power minus 3x to the second power. Let's do a quick check, make sure that's exactly the same. Yes, it is. And we're going to set that equal to 0. What I would recommend is to start yourself with the standard window. So push the zoom button. Standard is number 6. So here's zoom standard, and there's our function. We know w has to be positive, so this intersection here is not helpful. There's an intersection over there. Okay. Remember, this is a graph of the derivative. So if this is the derivative, then every time the line is below the x-axis, the derivative is negative. Every time the derivative is above the x-axis, the derivative is positive. So I'm going to zoom in over here. I'm going to do that with zoom box. Zoom box, I'm just going to draw the box that I want to see on the window. Move the cursor over to the lower left corner. Push the enter key. And we'll move the cursor to the upper right corner of the window we want to see. I wanted to keep that x and y axis into our window in our view screen. So here is the graph, and it's going to be a little easier to see that hopefully it's going to be easier to see that it's going from, the derivative is going from positive to negative. Calculate. I didn't get to calculate. Second, calculate. We're going to calculate the 0. of the graph. Where does the graph cross the x-axis? For a left bound, we just need to pick someplace here on the window where the derivative, or so where this blue line is to the left of the 0, and that would be right around here. Well, basically anything left to the left of this point. See, that point is at 1, 2, 3, 4, 5, 6, 7, 8. So why don't we go at 8 for the left? So I know it's between x equals 8 and x equals 9. On this calculator, you can see that this section, as long as we get the 0 in between these two vertical blue lines, we have ourselves our 0. The next one is a guess. Basically, just put any number in the middle there. I'll put 8.5, and it should come up with a 0 at 8.660. Let's take a screenshot of this. Okay, there's our critical value. And here it's easy for us to do that first derivative test. We can set up our table here. We've got the first interval from 0 to 8.660. And I'm saying from 0 to 8.660 since we're talking about a physical dimension. W should be greater than 0, comma. 8.660 to positive infinity here. Next, we'll examine S prime, and taking a look at my S primes here. Since my graph is the graph of S prime, I can see that to the left of my critical value, S prime is positive because the line is above the x-axis, and to the left, the derivative is negative because the line is below the x-axis. So that means I have a relative maximum and an absolute maximum since there are no other critical values. So it's our absolute maximum at W equals 8.6625. The last thing I'll need to do here is find a value of D. And let's take this function right here where D is equal to 15 squared minus W squared. And we can use that to find our value of D. So D squared is going to be equal to 15 squared minus 8.66025 squared. And with our calculator, we know this is going to be the square root of 15 squared minus 8.66025 squared. That gives us 12.247. So our dimensions are 8.660 by 12.247. And of course, these are inches. So let's put our inch marker at the end here. And that is our first question. Let's take a look at question 30 next. We've got one airplane is approaching an airport from the north at 200 kilometers an hour. A second airplane is approaching from the east at 160 kilometers an hour. Find the rate at which the distance between the plane changes when the southbound plane is 50 kilometers away and the westbound plane is 28 kilometers away. So let's try to visualize this real quick. We have an airport in the center and a plane at the north and a plane at the east. So I'm thinking this looks like a right triangle. So we've got our airport in the center here. Let's put an airport there. And, okay, now that I've created this as best as I can, we're going to figure out our distances. Now, the distance from the airport to the plane at the north, it's 50 kilometers away. And the westbound plane is 28 kilometers from the airport. We also know that the airplane approaching from the north is traveling at 200 kilometers per hour. And the airplane arriving from the east, i.e. the westbound plane, is traveling at 160 kilometers an hour. So the distance between the planes is currently unknown. We could definitely figure this out since this is a right triangle. If we call the plane distances x and y, then we can call the distance between the two planes z, and then x squared plus y squared equals z squared, or z squared equals 28 squared plus 50 squared. Let's grab our calculator. And so we know that z is going to be equal to the square root of 28 squared plus 50 squared, which gives me 57.306. I'm going to take this result and store this in the calculator as z. I don't know if it's going to come in handy or not, but at least I'll have it there. So z is going to be defined on my calculator the same way it's defined on my paper. Okay, the next thing to do here is to figure out how can we figure out the rate at which z is changing, because that's the distance between the two planes. The equation that ties x, y, and z together is that Pythagorean theorem. So if we have x squared plus y squared equals z squared, then if we take a derivative with respect to time, we should be able to get the rate at which z is changing. Note, of course, that we're taking the derivative with respect to time, and time is not the same as the variables in our equation. So we're going to need to use the chain rule in that related rates way. Okay, the derivative of x squared is 2x times dx dt. The derivative of y is 2y multiplied by dy dt. And the derivative of z squared is 2z dz dt. We can substitute here. We know from our diagram we've defined that x is 28 and y is 50. We also have a value for z. Z was at 57.306. Remember that even though I'm only writing 57.306, I do have that entire number stored in my calculator, so I'm not going to use this truncated version of the number. I am going to use the all the digits of the number, or as many digits that my calculator can hold on to. All right, the next things I can substitute here are dx dt and dy dt. dx dt is this 160 here. dy dt is this 200 up here. We can come back and put those values here. And I'm thinking about this, and I really should mention that these derivatives are negative because those values are decreasing. So we'll put a negative sign here on all of these. This means that dz dt is going to be negative as well, since the distance between these two airplanes is shrinking. I also kind of want to assure you that even if you didn't put these negative signs here, you would still get a numerical result, which is going to be the same. In any case, let's go ahead and take these values and let's see, we're going to solve. We're going to get that dz dt is going to be equal to this monstrosity of an expression here. I know some of you probably are kicking yourself because you want me to divide that 2 out. Not necessary, I don't think. Okay, let us put this into our calculator. We're going to give ourselves a fraction bar. We've got 228 negative 160 plus 2 times 50 times negative 200 divided by 2 multiplied by z. And now it's kind of handy that I kept z in that calculator. I'm getting negative 252.677. Great. Last thing to put here is a summary. Since we have a negative derivative, we're saying that the distance between the planes is decreasing at a rate of 252 kilometers per hour. Remember, I like to write a summary here that leaves speed as a positive number and suggests whether or not that number is actually negative or positive by using the words increasing and decreasing. So one more problem to do here, and it is the temperature in Malmö, Sweden. We have the temperature in Malmö, Sweden recorded for 8 hours, and we're going to use a trapezoidal rule to approximate this integral. And then we're going to, this says to estimate the average velocity of the car. I do believe that's a typo. What it really should say is that we're going to estimate the average temperature on this 8-hour period. All right, I think that's easily done. We're going to notice a few things. We're going to notice that the delta t's here, all of these, the difference between each measurement is a difference of 1 hour. So we have a delta t of 1 hour. Now that's an important fact for us because it means we can use the trapezoidal formula and we don't need to mess around too much with anything else. Put that in plain English, it means that I'm not going to make a chart here. I'm just going to use the trapezoidal rule. Okay, for the trapezoidal formula, we're going to multiply 1/2 multiplied by a very long sum. We're going to take the very first number, 19, and we're going to keep that alone. We're going to multiply all of the other interior numbers by 2. So 2 times 20 plus 2 times 22, 2 times 20, 2 times 18, 2 times 16. And now we've reached the right of the interval, so I don't need to multiply that one by 2. Basically, all of the interior values are multiplied by 2. The only ones that are not multiplied by 2 are these exterior ones. Now, the only thing I forgot to put here is my delta t. Sorry about that. My delta t here is going to be 1. Okay, I thought it'd be a good idea if I left that formula there. Let us calculate this using our TI. We'll put our 1/2. Our delta t is 1. We're going to multiply, we're going to do 19 plus 2 times 20, and then all the way down the line, all the way down to the very last 16, and we get 311 over 2, which you probably want as a decimal, so let's turn that into a decimal. That is, take the previous answer and convert it to a decimal. And that's 155.5. Therefore, the average temperature is, we're going to take our integral and divide that by 8. See, yeah, we're going to put a 1 over 8 minus 0. And that's going to be equal to 155.5 divided by 8. Take that response, divide by 8, and it looks like 19.4375. Okay, that takes care of the first part of the calculator section for your final. We'll see you in the next video when we tackle the last, I think there were 3 questions of your final. See you next time.